Now, in this section, I'd like to show you a really interesting technique of how we can basically transform a load along a transmission line. And what I mean by that is that the Smith chart is such a powerful tool that given a load whose value is equal to ZL, I can very quickly find out what is the load at some distance L from my load along a transmission line with impedance of Z0. That happens all the time. It's a very, very common thing to transform a load through an impedance. In fact, for a very simple scenario, we already know the answer. We have already seen, for example, the answer when we have a lambda by 4 transformer. So when this is lambda by 4, we already know the answer. The answer is Z0 square over ZL. But if the distance is not lambda by 4, it's something more generic, then the real equation is actually shown for you right here. So it's a very difficult equation to basically even visualize. Look at this. ZL depends not only on the number gamma L, but it depends on this exponential here. And this is an equation we derived before. So the brilliancy of the Smith chart is that it gives you a very interesting way to simply visualize this seemingly complex equation. So here's how this works. If I basically write down, as we have done before, that gamma L times e to the negative j2 beta L is equal to this reflection coefficient gamma as a function of L, then essentially I end up with the same equation that I started with. Remember that I started with an equation that said that ZL is 1 plus gamma L over 1 minus gamma L. So I basically have exactly the same thing, except now my reflection coefficient gamma L has this exponential right next to it. So it's here written clearly, so you can see that. So what does this mean? It means that I can still read my load if I only replace my gamma L that I was given with this more complicated gamma L. But what is this exponential e to the negative j2 beta L? This is nothing else but a phase change. So all I have to do is basically shift my phase by an angle of negative 2 beta L, where again L is the length of my transmission line, lambda by 10, lambda by 2, lambda by 20, whatever the case might be, and beta is basically 2 pi by lambda. It's the phase constant of my transmission line or propagation constant. So, in other words, what this equation really tells you is that go to the gamma L that you had on the Smith chart, rotate, that's what we do for a phase change, rotate this point by an angle that is equal to 2 beta L, actually negative 2 beta L, and then you'll be able to get a length lambda away from the load. So let's see that graphically. So we can go ahead and experience this. So here's my Smith chart, and here's an example of a load ZL. My goal is to find out what happens at distance L away from that load. So as we just discussed, the gamma L as an absolute value, meaning the magnitude of gamma L, will be the same. This is exactly what you saw from the previous equation right here. The gamma L magnitude will actually be the same, only its phase will change. So since the phase is indeed changing, I have to change my phase by negative 2 beta L. So now I have to rotate. But the question is, do I rotate this way, clockwise, or do I rotate this way? Well, Mr. Smith actually thought about that, and he constructed the Smith chart such that any movement away from the load is actually clockwise. Except he didn't call that away from the load, he actually called it towards the generator. Because in his mind, there is some generator somewhere here that you're basically moving towards when you're moving away from the load. So when you go on the Smith chart, you basically move clockwise anytime you move away from the load, or anytime equivalently you move towards the generator, and counterclockwise the other way. So that means now I'm going to basically rotate myself with an angle of 2 beta L clockwise until I basically am satisfied. So let's say that this is the angle 2 beta L. So my load will go from this point along the same circle and will end up on this point. And this point here is my input impedance Zin. So this is a very, very quick calculation. You can do it just literally by drawing the circle. But as I mentioned, even more importantly is to have this mental picture in your mind, that when you move along a transmission line, any load, essentially what you're doing is you're moving them on a constant gamma L circle. Now, one thing I do want to emphasize a little bit here is what happens if I have a lossy transmission line. So if I do have a lossy transmission line, not only I will have this negative J 2 beta L, but I will also have an attenuation constant alpha L. So if that happens, then I will have to add here an e to the negative alpha 2L. And that means that if I were to do this thing in real life, I would not move on a circle that is constant radius, magnitude gamma L, but rather that radius would be reduced by e to the negative alpha 2L. So in real life, you're not exactly in that circle, and I'm going to exaggerate here. You're actually going to spiraling down, and you will end up here. And that new distance is basically gamma L e to the negative alpha 2L. Now, we won't really focus on this part in this class, but I do want to mention that essentially in real life, you end up with a slightly smaller circle. So what is really important to remember here? What's really important to remember here is that you're simply moving on a constant gamma L circle whenever you're basically moving along a transmission line, and that way you can essentially reach any type of load that you want. Now keep in mind that the angle is 2 beta L, not beta L, which basically has some interesting cases. For example, when I am moving by a distance of lambda by 4, the equivalent angle I'm moving is actually 180 degrees. So if this was really a lambda by 4 transformer, I would basically come to the antipodal point right here. Also, when the distance is lambda by 2, the angle 2 beta L is 360 degrees, which we also expect, as we learned before. Anytime you move lambda by 2, you basically come back to the same point that you started with. Of course, the phase of the voltage and current are still 180 degrees apart, but the impedance is identical, and you can clearly see this with the Smith chart. In other words, a lambda by 2 rotation means full rotation, 360 degrees on the Smith chart. A lambda by 4 rotation means the antipodal point right here.